So Andre, if you want, we can slowly start.
Okay, yeah, I'll introduce myself and yeah, take it easy.
All right, thanks.
All right, well, in the first place, thank you for
Andre, if you
inviting
want,
me.
we can slowly start. Sorry.
Do you hear
Go
me?
ahead. Go ahead. Yeah, perfect.
Okay. Yeah, I just wanted to start by thanking you for giving me the opportunity. And I wish I could be in Istanbul, but I guess online makes things much easier. Um, and I realized that I believe many of you work on accreting millisecond X-ray pulsars. So I normally work on super Eddington accretion and basically trying to bridge the gap between what we see close to the compact object with the large scale environment. So I will be talking about the nebulae, but I figure maybe this other project I'm working on will be more interesting to you. And I'm hoping also to get some feedback from, because I'm sure you will be more knowledgeable in some aspects. And the key idea here is that we thought that we know from millisecond X-ray pulsars that accretion buries the magnetic field and spins the neutron star. So what about ultraluminous X-ray sources? We would expect this process to be much stronger. So the idea is to study that and see what can we learn from it, basically. Okay, so here's a bit of outline. So I will start discussing or making the case for why we think ULXs are actually binaries accreting at super Eddington mass transfer rates. And then I will tell you a bit what we know about the neutron stars that have been identified recently in these systems. And then I will explain you our prescription to model the evolution of the spin and the magnetic field. So we basically need to prescribe three things. So one is the mass transfer rate through the disk. The other one is how the field decays as you accrete matter. And then is the torque on the neutron star. And then I will show you some early results and some modeling we've done of some notable ULXs. And I must say this is also work in progress. We have a paper that should come out in fairly, or it's in quite advanced state, let's just say. But yeah, there's still some preliminary results, basically. Okay, so around the 1970s, it was the first time that we could finally resolve the outer galaxies in the X-ray band. And what they noticed is that actually, when you look at these galaxies, in many of them, you would find these extremely bright objects. So here is a Chandra image of the galaxy you see here in the optical. And separated from the nucleus of the galaxy, so you can see here at the center, there's no active supermassive black hole. They would spot these point-like sources with luminosities in excess of any binary seen in the galaxy. And we typically find 1 to 3 ULXs per galaxy on very roughly. And then the idea is that to set them apart from what we see in X-ray binaries, where we knew the most massive black hole is around 20 solar masses. So they define them as point-like sources that have a luminosity above the Eddington limit of a 20 solar mass black hole, which is basically 10 to the 39 ergs per second. Now, there are two possibilities to explain this abnormally bright luminosity. You have two levers you can pull. So either you increase the mass of the object, and because we know the Eddington limit scales linearly, that's sort of a natural way to explain these systems. So these ULXs then would fall between these black holes that sit between those form as the endpoint of stellar evolution, and those we see that have grown through cosmological timescales as the supermassive black holes we see today at the center of most galaxies. However, when we look at the spectral properties of ULXs, they don't really behave as we would expect if you simply scale the mass of the system. There are some good candidates that do show this behavior, but in general, we find that we can rule out this scenario based on the spectral and timing properties, basically. So the other option is to increase the mass accretion rate. Now, you may all be familiar with the standard picture of accretion, also called sub-Eddington accretion. So in the seminal paper by Shakura and Sunyaev, basically they derived the formulas for the thin accretion disk. And what they assume is that the mass that is transferred by the star is conserved throughout the disk, and it's what makes it to the black hole. And then that all the energy is radiated locally. And in this picture, we know the accretion luminosity grows proportional to the mass transfer rate. And then what you can do is, based on some efficiency, you can find what is the mass transfer rate you need so that your accretion luminosity reaches the Eddington limit. So when the luminosity or the mass transfer rate is below this threshold, we typically talk about sub-Eddington accretion. But then when we go beyond this threshold, then the picture changes. And the main thing that changes is that the radiation in the accretion disk starts to affect the dynamics of the accretion flow itself. So there are two main effects. So, the first one is that because the radiation pressure will help to sustain the gas in the disk. So therefore, you will get a puffed up of this with an increased scale height. And what can happen is that the diffusion time for a photon to escape the disk can be larger than the accretion time scale. So what this happens around black holes is that some of the photons get advected into the black hole before they get a chance to escape. And the other effect, and more importantly for us, is that because due to the radiation pressure, some of the material can become unbound and be launched as a wing accelerated by radiation pressure. So what this makes is that the accretion no longer grows proportional to the mass transfer rate, but you have like a saturating effect. Because even if you dump more material, some of it will either escape the disk or be swallowed by, sorry, I should say the luminosity will be used to accelerate some of the material, or will be swallowed by the black hole before it has a chance to escape. Now, what I will discuss throughout this talk is something we call the spherization radius. And this is a radius at which the disk reaches the local Eddington limit. And what happens is that within this radius, some of the material, as I was mentioning, can become unbound, and this is where the wind happens. Now, the result is that the mass that is transferred by the star is no longer the same that makes it to the black hole. You will have some material lost as an outflow, as I was mentioning earlier. Now, do we have some evidence for these winds in ULXs? And in my opinion, the best piece of evidence we have is in the form of optical or radio bubbles that we see around a handful of these systems. So here's an example we discovered with Muse. And you can see the shear scale of this bubble, basically this ellipsoidal structure. And you can make some energetic and size arguments to rule out these as being supernova. They are just too large. In fact, I think the largest supernova remnants are on the same size as this circle, or I will show it later, actually. And then the consensus is that these are inflated by the accretion disk winds slowly over time. And in fact, we put this hypothesis into very strong footing recently, because it was the first time that we discovered a bubble, shock ionized bubble by the winds, in a system where they had discovered highly blue shifted absorption lines in the X-rays using the high resolution gradients in XMM. So it was the first time where we could sort of relate what we see close to the compact object with what the larger scale impact. Now, the other cool thing we can learn about this nebulae is that basically we can measure the expansion speed, we know the size, and you can just get a very rough idea of how long this system has been basically dumping material in the environment, or in other words, the accretion timescale, basically. And what you find is that to explain this nebulae, you typically need an accretion timescale of the order of mega years. And in fact, this is consistent with what we see, or what we find from binary synthesis population studies. So there is, or basically we have a good evidence to show that super-Eddington accretion can be a sustained process, basically. Now, the other basically nail in the coffin that sets ULXs as super-Eddington accretors, and the reason why I'm here today, is that we found pulsations in some of these systems, which undeniably proves the accretor is a neutron star. And today we know around 9 of these systems, although the number keeps growing every year. And there's a very nice statistic in this paper that claims that for all the sources for which we could have detected pulsations, we have detected them in 25% of neutrons we have confirmed that 25% are neutron stars. So that's sort of a lower limit on the number of neutron stars that are in ULXs, basically. Now, the other piece of evidence that tells us something extreme is going on beyond the luminosities is that when we look at the spin-up rates, they are also far larger than what we see in X-ray binaries. So this is another piece of evidence that is telling us that the accretion material is not only producing these extreme luminosities, but also spinning up the neutron stars. So this is a very strong indication that, again, something extreme is going on in these systems. Now, there is another phenomenon I want to tell you about, which will be relevant later, which is something known as the propeller transition. I'm sure most of you are familiar with, but basically this occurs when the magnetospheric radius, which is where the magnetic pressure and the ram pressure of the gas balance, is larger than the corrotation radius. And what happens is that the disk does not rotate fast enough to latch onto the magnetosphere. And basically, the centrifugal barrier expels the material. So we have, or to me, this basically there are two observables you expect from this process: is a drop in luminosity, and then that the period of the neutron star will start to increase because you just have a spin down mechanism from the slow parts of the disk, basically, as you stop accretion. So here what I'm showing is one of these ULXs, actually is the brightest one that we know. It has also superorbital periods, so this is the X-ray light curve, although I won't be discussing that. But what I want you to focus is here, we see the flux dropping. This is a Chandra upper limit. You can see how low it went, and then it comes back up. And you can see that as the source is bright, the period is decreasing, but the moment the source drops in luminosity, you see the period coming back up. So to me, this is a strong signal that accretion is being halted. And what is neat about this process is that we can infer, or we can get an estimate of the magnetic field of the neutron star, because we know that when this happens, the magnetospheric radius needs to be equal to the corrotation radius. Right, so in the presence of neutron stars, I've given you a picture of super-Eddington accretion, but how does this change when we have a magnetic field? And the answer here is complicated, and in fact, the field is divided as to what happens exactly. But basically in this cartoon, I will try to give you a brief overview. So this is the companion star. Here the disk is thin. And then when the disk reaches the local Eddington limit, then you have this increased scale height due to the radiation pressure. You have some outflows. And then what you can envision is that if the magnetic field is weak, then the magnetospheric radius will be within this portion of the disk. So at some point, the disk will be truncated, and then the material will be forced to follow the magnetic field lines. Now, in this scenario, and some proponents argue that this is the case, and then what you have effectively is that the emission within the super Eddington part of the disk is being collimated toward the observer by the funnel I showed earlier, basically. And then the other sort of view is that actually the magnetic field is very strong to the point where it's truncated before the disk can reach the Eddington luminosity. And in fact, there is a good argument to be made here, because we know in the presence of strong magnetic fields, the electron scattering cross-section decreases. So that allows you to basically increase your effective Eddington limit. And in fact, what I will argue later is that maybe it's both. Maybe as the system evolves, you can start with something like this and then evolve to something like this as the magnetic field weakens. Another thing I would like to bring to your attention is that something that has been, I feel, overlooked in the community is that actually when you are in the super Eddington regime and you enter propeller, you can still have a very bright system. So because if the magnetic field is weak and most of the luminosity is coming from the accretion disk, then even if you suppress the parts within the magnetospheric radius, you still have a very bright disk. And in a recent paper, we show that depending on the luminosity drop, or basically the magnetic field will dictate the luminosity drop that you will observe. And this can range from basically 2 orders of magnitude, in fact. Okay, so with that introduction, I would like to basically emphasize some of the open questions on the field and some of the things I will be discussing after with my work, basically. And a big open question in the field still is, what is the exact fraction of black holes to neutron stars? And this basically hinges on this other question, which is, okay, is it the case that there's a lot of neutron stars and we just don't see pulsations? Or is it the case that we're actually seeing the neutron stars and the rest are black holes? And in fact, there's been various attempts to try to see this through the X-ray spectral properties. So this is like a broadband spectrum with XMM and nu star. But the thing is that from a spectral point of view, there's very little difference. So this has been taken as an argument to say that perhaps most of them are neutron stars, and there is some reason why we don't see pulsations. And then the other big question I mentioned is that it is still unclear whether are we dealing with a population of strongly magnetized neutron stars, and is this what sets them apart from binaries we see in our galaxy? And then how does the accretion flow geometry change depending on our assumption on the magnetic field? Okay, so as I said earlier, our work was sort of inspired by what we see in regular pulsars in our galaxy. So as you're familiar, when we look at those that accrete via Roche lobe overflow and the millisecond X-ray pulsars, we know that these pulsars have been spun up by the accretion process, and their magnetic fields have been buried or suppressed compared to those young radio pulsars or even some those that we see in high mass X-ray binaries. So if we know this is happening, then what we should expect in a super Eddington accreting system is that this will happen much more strongly, basically. And in order to try to answer that, what we need is we need to prescribe three things, basically. We need to prescribe how much matter makes it to the neutron star and goes to bury the magnetic field lines, the magnetic field, sorry. We also need to prescribe how does the magnetic field react to the additional mass accretion rate, basically. And then how is the neutron star being torqued by the accreting or by the accretion disk. And then you can think that this is a very highly coupled system, because for instance, as you decrease the magnetic field, you will start to decrease your magnetospheric radius, right? And you can have a situation where basically you go from a system that has a super or a thick disk. Oh, sorry, the other way around. You can go from a system that has a thin disk to one that has a thick disk, and so on. So solving this requires basically taking into account all these pieces that sort of depend on each other. So what I will do now is basically walk you through our prescription for each of these things and how we've put them together and try to see how the system evolves, basically. Right, so as I was mentioning earlier, what we have is the thin disk in the outer parts of the disk. And then as you reach the Eddington luminosity, you have the spherization radius, and within this part, we have some mass that is lost due to the outflow. So what this means is that the effective mass reaching the magnetospheric radius will be lower than what you started initially. And then another effect we take into account, which is still very unclear, is that we think there should be a similar Eddington limit in the accretion column as well, where you have this balance between magnetic pressure and radiation pressure. So based on calculations from Alexander Mushtukov, we also take into account the fact that not all material can make it to the neutron star. Some of it will also be expelled in a wind, presumably. So that's for the case where the magnetospheric radius is larger than the magnetospheric radius. And then we have the other case, where here instead you don't have any mass loss, but you still have this mass that is lost to the because of the radiation pressure. And I should say that this balance depends on the magnetic field. So a stronger magnetic field will be able to withstand more material or a larger radiation pressure, so to speak. Right, so having explained that, now I'm going to move to how we prescribe the decrease or the burial of the magnetic field. Now, I have to say that this is still very much research in progress. When you look at the various papers, there's very many mechanisms being proposed. We took some ideas from this paper, where basically very briefly, as the material is accreted and sinks due to the gravity, then it will drag, because the magnetic field is frozen into the plasma, it will drag the magnetic field lines. And this distortion will effectively decrease the dipole component of the magnetic field. So that's one of the basically ideas we took from. There are other mechanisms. So we have basically looked into these three set of prescriptions. So you have one that was basically adjusted to X-ray binaries. So this is purely from an observational point of view. there's a more analytical approach. And then there is this the process I just described, where they employ numerical simulations to get well, to derive how the magnetic field changes with the mass accreted onto the neutron star. And you can see there's a wide range of possible decays. I should say also that this Zhang here, I'm showing the limited case. So this is basically our most conservative bound, basically. Okay, and now I will focus on the torque on the neutron star. So what we have used is some ideas from these papers you see here. The basic idea is that in a disk, you have certain portions within the co-rotation radius that spin faster than the neutron star, and you have the outer portion that's spin slower than the neutron star. So you have some portion of the disk that are spinning up the neutron star, and then some portions of this are spinning down the neutron star. And then depending on the magnetospheric radius, the co-rotation radius, then you will have a different balance. Now, this also applies when you go into propeller, and you will have a spin down torque from the outer parts of those beyond the magnetospheric radius, basically. So just to give you an idea, maybe in the early phases of the accretion process, you can have something like this. So as I mentioned, you have a very strong magnetic field. You don't have mass loss in the disk. And then you have a large torque because your magnetospheric radius is very far from the neutron star. And then a slow decay because the magnetic field decay is proportional to the magnetic field itself. But then at the later phases, as the magnetospheric radius decreases, because the magnetic field will decrease, then you may transition to something like this, where the disk finally develops this thick part with the radiation pressure. And in this case, you will slow down the spin up because the magnetospheric radius is much closer to the neutron star. So here are some of the results. So in the top panels, you have the spin of the neutron star. And in the bottom panels, you have the fastness parameter, which basically tells you how far you are from spin equilibrium, which is this situation where basically the torques balance and the period is stable. And then here's for a low magnetic field, for a stronger magnetic field. And then the solid and dashed lines show two different mass transfer rates, basically. And the first thing is that so the stronger the magnetic field, the stronger the spin up will be at early phases, but you enter spin equilibrium also much faster, and that sort of dampens the decay of the spin, basically at after 10 or 50 years, basically. And then you can see also that the solutions, or an interesting result as well, is that the solutions become independent of the initial spin period, because most of the torques depend on the spin itself. So basically what you find is that the evolution will basically converge regardless of the initial spin period. Now, the other thing I wanted to highlight as well, I mentioned this object early in the beginning, where we presumably know the accretion timescale and we know the spin period because it's a neutron star, and we failed quite strongly to reproduce that system. So either there is some other mechanism that we're missing, and maybe there is some spin down due to the wind that could slow down the spin evolution compared to the case shown here. Or it could be the case that this system underwent periods of propeller and it was not continuously accreting. Now, the other thing we also derive is the decay of the magnetic field. So this is what I show here for the three prescription laws. And one notable feature is that this is independent of the period, so that makes the problem much easier. And the idea is that, again, as you decrease the magnetic field, the decay becomes accelerates, basically. And what we find is that the mass accretion rate that makes it to the neutron star is mostly controlled by this, by the balance in the accretion column. Basically, that's what sets the material making it to the neutron star. But you can see that in about 1,000 years, then the magnetic field will be strongly suppressed unless you invoke the most conservative decay law, so to speak. The other thing that we also produce are the luminosities. So here you have, again, for the 4 cases, so low magnetic field, low mass accretion rate, low magnetic field, high magnetic field, stronger mass transfer rate. And then what we find is that we do not need to invoke any beaming, as has been suggested in the literature, to explain the ULX luminosities. Very easily, we can reach 10 to the 40 ergs per second, which is basically what is observed. And then also very important is that the magnetic field is basically the most important factor in setting the luminosity, because most of the radiation comes from the accretion column and not the disk itself. Right, so what I will move on now is to the modeling. So there are a few ULXs for which we have been able, or other researchers have been able to track the spin period of the neutron star as a function of time. And we've taken our models and tried to see whether we can explain the evolution. And so there are 4 parameters that we can play around. So it's the mass accretion rate, the start time of the accretion process, the initial period, and the initial magnetic field. But as I said, because the solutions are basically independent of the initial period, this is a parameter we cannot infer. But basically tweaking these parameters, we have tried to reproduce the evolution of some ULXs for which we have this data. So the first system is NGC 300 ULX1. This was identified in 2010 as a supernova, actually, by an amateur astronomer. But then in 2016, it was seen that it reached a luminosity of 10 to the 39, and they discovered pulsations, which set the system as a neutron star, basically ULX. And it is a record holder in terms of spin up. In a matter of 4 years, we have seen the period decrease from 120 seconds to 20 seconds, basically, which is unheard of. And then the companion star was identified as a red supergiant. So here you can see the luminosity, basically, and here is the frequency, or the spin frequency, basically, of the neutron star, and you can see how it's going up. Now, one interesting aspect of this system, which I won't discuss in detail, is that even though we saw the luminosity dropping, you can see that the spin frequency continued to accelerate. And this sort of implies that accretion cannot have been halted. And the idea is that maybe there has been some obscuration as opposed to a halting of accretion. So here are the results of the modeling. Now, I will say that, well, let me introduce the plot first. So here is the period, the luminosity, the fastness parameter, and the magnetic field. And each track has been taken from a posterior distribution. So we do an MCMC, and then we can see, okay, which are the actually valid parameter ranges, basically, if you want, and how do the different tracks differ. And one thing I want to bring to your attention is that we only feed the periods and not the luminosities. So you can see that we can reproduce the periods fairly well, and the luminosities come out naturally of the model in the range that are observed. So this means we don't need to invoke any beaming in this system. And then what we find is that the accretion started very early. We cannot reproduce this system if, let's say accretion started 10 years ago or 100 years ago. So our modeling naturally shows or produces or supports basically a young accreting system. And this is in line with the fact that it was discovered in 2010. So we think this system just sort of was born, or we saw the first light of the accretion process, basically. And then the magnetic field we estimate is between 10 to the 10 to 10 to the 12 Gauss. Now, the other system we have modeled for which there was data is M82X2. This was the first pulsar that was ever discovered, and it was shown that it's close to spin equilibrium, or at least that's what they think. Then the luminosity in the X-rays from 10 to the 38 to 10 to the 40, so it varies quite substantially. And then what was interesting is that despite the system being discovered in 2014, and then there was huge work by Matteo Bacchetti with a NuSTAR campaign trying to track the spin frequency over time. Actually, I forgot to quote the reference here, is Liu et al. 2014, I think. He went back to the Chandra data and the XMM and discovered that actually prior to this discovery and detections, the neutron star was actually spinning down. So we have all this data that we can model. And once again, here are the results. So this is the period as a function of time. Here are the different tracks from the posteriors. And then what is very interesting about this system is that our modeling suggests it just came out of propeller, basically. The magnetic field was so strong that there was no accretion happening within the magnetospheric radius. And then close to the first measurements, the neutron star may have started accreting. So this explains the spin down, basically. And what we predict is that it will enter spin equilibrium very quickly. And then the magnetic field that we find is of the order of 10 to the 13. So very strong magnetic field. And again, we find that this system may have started accreting as early as 200 years ago, something like that. So fairly young again. And the last system we have modeled is P13. Oh, sorry. So here you have the light curve. This system, again, as another one I showed earlier, shows a superorbital period. This is the UV light curve, X-ray light curve. And it's a similar case as the one I showed earlier. Even though we see the flux going down, we see the period still decreasing. So again, there is this idea that probably accretion is continuing despite the X-ray flux going down. And here's again our modeling. So what we infer once again is that we cannot reproduce it if we set the accretion or the first accretion episode, let's say 1,000 years ago or 10,000 years ago. Again, we find something fairly recent. Once again, we can produce luminosities in the observed range without putting them in the modeling and without invoking any strong beaming. And we find a magnetic field of the order of 10 to the 12, basically. And we would support from the range observed here, you can see that, so if you see the very dark curves here, they underpredict the luminosities. So from the luminosities, we could support the magnetic fields on the higher end of the full range derived here. Okay, so that's about the modeling. There was one last thing I wanted to mention that we also looked at. And if you remember this system I mentioned earlier, where we find this evidence of propeller, because unlike the other systems, there has been spin down during the disappearance of the flux. And then what we have tried to do is, so we have produced the tracks I showed earlier of magnetic field, period. And then when the system enters propeller, we know the mass accretion rate must have decreased, because when the mass accretion rate decreases, the magnetospheric radius expands, and that's what triggers the propeller. So we can then ask ourselves, okay, what fluctuations do we need to see this propeller? And the fluctuations, they cannot be, we know accreting systems, the mass accretion rate fluctuates, so you cannot make arbitrarily large, basically. So what I show here is the top panel shows the magnetic field, the spin period in yellow for two different values. So we've seen this earlier, basically in different plots, but most important is the bottom panel. So in the cyan, you see the magnetospheric radius, and in yellow, you see the corrotation radius. And you can see that because the mass accretion rate fluctuates, the magnetospheric radius is moving, basically. And you reach a point where these fluctuations are enough to push the magnetospheric radius beyond the corrotation radius. So every time you see a small spike here, which I highlight here in the panel, or I try to, that's when you have propeller. But if you set the magnetic field much lower, then even though your magnetospheric radius fluctuates, it is so far from the corrotation radius that you cannot trigger propeller. So we think this is a good argument to suggest that the magnetic field in this system must be at least 10 to the 13, basically. Okay, so with that, I reach my conclusions. So what I mentioned earlier is that we have tried to, from inspiration from the accreting millisecond X-ray pulsars, try to extrapolate that to the super Eddington regime. And what I will show is that the spin-ups and the magnetic field decay is extreme. And basically, after a period of 10 to the 4, the magnetic fields can be already below the second mark. And I think the main key takeaway I want you to take is that from the modeling and from the tracks I showed earlier, there has to be a population of neutron stars that are fastly spinning and with magnetic fields heavily suppressed, to the point where we can only detect ULXs in a very brief window, so to speak. So that those for which we see pulsations, I would argue those are sort of the tip of the iceberg. We're just detecting a very small fraction, and there can be like basically a population that will go undetected with current instrumentation. Now, we had some problems reproducing this ULX with the nebulae, where we think we know the accretion timescale and the period. So I think some mechanism can be at play. So maybe if the magnetic field couples with the wind, then you would have an additional spin down mechanism. Or perhaps the system went under periods of propeller, this assumption of continuous accretion is not supported. And then the next thing we would like to do is to take this code, try to do some binary population synthesis studies, and see what fraction of ULXs we should observe and how many we should be able to detect, basically. And that was all. I hope that was of interest to you, and I'm very happy to hear your feedback.
Thank you very much. That was really nice. Are there any questions? Let me ask.
May I ask a question?
Sure, go ahead, Yavuz.
So you are using the Super Eddington regime. You're considering the Super Eddington regime, and you mentioned that mass flux catches a logarithmic term in the presence of this Super Eddington regime. And in that case, the ramp pressure also is affected. It decreases. And actually, the magnetospheric radius also changes from the classical Alfvén radius, right? It differs from the classical Alfvén radius. In the classical Alfvén radius, you have the exponent 2/7, right? But in this case, you would have 2/9, I guess. Yeah, and then, this magnetospheric radius adjusted to this Super Eddington regime. Are you using this one, or are you using the classical Alfvén radius in your calculations?
I actually went over that, but yes, we do account for the full the fact that you have mass loss, and therefore your magnetospheric radius is adjusted. Basically, less mass reaches the magnetospheric radius, depending on where your spherization radius is. So yeah, we fully take into account that, basically. Yeah.
Okay. And also in the classical case, where it is a sub-Eddington, you have a certain relation between luminosity and torque, which is like to the 6/7th power. Right? Now, this should change. And maybe you can confirm this. Right? It's going to change from 6⁷ to something else.
Yeah, I haven't looked at. I could easily check how the torque. So you're saying that how the torque varies with the luminosity, yes?
Yes.
Yeah.
So this would be different in the case of Super Eddington regime compared to the sub Eddington regime. The scaling exponent would be different.
Yeah, absolutely. So yeah, it's something maybe I don't have explicitly written, so to speak, but it will come out naturally of the full, this very highly coupled thing. So for sure, it's something I could look at. Yes. Thank you.
Thank you.
Any other questions?
I have.
Go ahead.
Thank you for a nice talk, Andreas. You mentioned that the optical bubbles indicate the accretion process can last for mega years, right? So according to your magnetic field real models, is this accretion continuous for like millions of years, or does the magnetic field decay infinity, or is there some limit?
There is for sure a limit when you reach the neutron star surface, basically.
Yeah, okay.
Yes.
Okay.
Yeah.
Also, the overall lifetimes of these systems are mostly dominated by the, massive binary companions, I guess, right?
Yes.
So there's one in the chat kind of related, maybe. How many non-pulsed ULXs would be there in total, I guess, in the...
Yeah, so the catalog, so from the catalogs, we know around 1,800, something like that.
Already, wow.
Now, of course, so those catalogs have I think I want to say between 10 and 20% contamination, because so a big problem is you just see a point-like source, in the X-ray is very bright, and you associate it with a certain galaxy just by looking at the sky, but that's not guaranteed to, it could be an AGN for which you don't see the galaxy, or maybe in a foreground star. So there's some kind of contamination there. But then I guess so that's the answer. But then from, bear in mind, many of these are 100 megaparsecs away. So many of these we cannot really study in very good detail. I would say those within 20 megaparsecs are the ones that we can, study in detail, and I wouldn't be able to tell you how many of those are
All
within
right.
that distance. Yeah.
No, it's fine. I guess the number already increased up to thousands, then, right?
That could be. Yes.
That's already too much. Anyway. All right. Thank you very much. Are there any other questions?
Yes, can I ask a question
Sure,
also?
sure. Go ahead. Sure, please.
Yeah, you said that the next step will be to simulate a binary star population. What kind of donor star are you going to use? Low mass or high mass?
I think
Extra binary.
Right. I wouldn't necessarily tweak the binary, the companion, so to speak. I would just let the I mean, I'm not that I'm super familiar with these codes, but just let some star forming rate, and let's see how many companions of each category appear. Now, maybe related to your question is what system leads to a ULX like system, and that's someone was mentioning that earlier, that so typically, basically the stable branch is when you have a high mass companion or an intermediate mass also, but then you can have some exotic or other flavors where you get a transient system. So I think you can get, for instance, a neutron star with a helium companion, and that would give you like a transient system. And so what classifies
mainly high mass X-ray binary. Mainly, do you think high mass X-ray binary?
Yeah, that's general. Yeah.
Okay, thank you.
The high mass undergoing a Roche law, basically overflow.
Oh. All right, thanks a lot. Any other questions? Last chance. And thank you very much for this really nice talk.
Well, thank you so much.
Pleasure. Just let us know when you somehow fly to Istanbul, okay?
All right. Yes, I will. I really, I was there long ago and I loved it. So yeah.
Oh, okay, cool then.
Wouldn't mind to go back.
All right. Thank you very much. Bye.